We are going to discuss about the topic called synchronous machines. Okay. As far as GATE exam is concerned, this topic is very, very important. Okay. Not only in electrical machines, this topic, synchronous machines, is also important for the subject power systems. Okay. So if you want to understand the topic called power system stability, the concept for this machines is important. Okay. So we will see the basics of synchronous machine in this particular video. Rather, we can say that we will have a general idea. We'll get the general idea of synchronous machines in this video. Okay. So as far as the name is concerned, synchronous machine, how is it different from induction machine, induction motor? So induction motor is very, very familiar, and in GATE also we have, and we have also done in the earlier videos, we have done that induction motor. So this induction motor, we know it is asynchronous machines. Why? Because the rotor will not rotate in the synchronous speed. Now there are some prerequisite of which you should know, some topics which you should know before looking into this synchronous machines, which I have covered in earlier videos. Like what is rotating magnetic field and what is synchronous speed. So we all know that, or what we should know, that a rotating magnetic field can be produced by a polyphase supply and polyphase winding. In this particular case, we will have three-phase supply and three-phase winding. So if we have these two basic arrangements, we will have a field which will rotate in the air gap or the circular structure which we will produce in the windings, okay, in the stator. Basically, we give this windings in the stator. So whenever we have three-phase windings and we give three-phase supply to that particular winding, we will have a rotating magnetic field, which I have explained in the earlier videos. So please, you can refer if you have difficulty in understanding the concept or the visualization of the rotating magnetic field. Okay. Now, rotating magnetic field is present in induction motor also. So the stator basically is same for synchronous machines and induction machine. So the actual difference is the rotor. In induction motor, we have two types of rotor, that is squirrel cage and wound rotor. And in both the cases, the rotors are short-circuited. Or, for example, in squirrel cage, it is short-circuited, and in wound rotor or slip ring, there are three-phase connections will be there, but ultimately the slips will be short-circuited. Okay. Here, in synchronous machines, there are two types of rotors. First one is cylindrical rotor. Second one is salient pole rotors. And both these types of rotors, we have some DC supply we have, okay, or DC excitation, and some field is produced by the rotor itself. Okay, the synchronous machines is also known as doubly excited machines. Okay, so if we can represent it graphically, the rotor that we can show, suppose this is the cylindrical rotor and this is the stator which will be outside. Okay, now this rotor is cylindrical in shape. Okay, that's why the name cylindrical rotor. Now in this rotor there will be slots. Okay, now due to these slots, now windings will be there and DC supply will be there in this particular slots, due to which we will have poles created. Okay, north pole and south pole will be created in the rotor. Okay, and now this rotor will be connected to the shaft. So this is this is how we can visualize a cylindrical rotor. So this field that is created by the rotor, okay, that is called flux field. Similarly, in salient pole, what will happen? A visualization of a salient pole will be something like the basic visualization. It is not actual. I'm just giving you the basic visualization. So here what will happen, the windings will be on this side in this way, and due to which North Pole and South Pole may be created, okay, due to the rotor, due to which there will be field, okay, rotor field, or this particular field excitation is given from the rotor. Okay, so this is the two different types of rotors that we have. Okay, now see, the basic difference between these two types of rotors is that in cylindrical rotor, in any cross section, in any path of the cross section, you see the reluctance is same irrespective of the position of the rotor. Irrespective of the position, the reluctance of any path is same. Okay, whereas if you see the salient pole, so this is the D axis and this is the Q axis. So the reluctance will be minimum in the D axis and it will be maximum along the Q axis. Okay. So here the reluctance depends on the position of the rotor. Okay, so this is a basic difference between the two rotors. Now since there are difference between the two rotors, so we have to analyze both the rotors in a different way. Now as far as gate is concerned, okay, the analysis of cylindrical motor or cylindrical rotor is very, very important. The analysis of salient pole rotors is not as important as compared to cylindrical rotor, but there are some topics which can be asked from this particular rotor. Also, it is very difficult. Actually, it is very difficult to analyze the flux orientation of the cylindrical rotor. But yes, there are techniques. Okay, so we will see that particular thing later. For now, let us concentrate on cylindrical rotor. Okay. So you see, operation principle wise, they are not different. But while you do the analysis, it will be different. Okay, that's what I want to say. So let us understand the operation also. So operation is something like, this is how it operates as a, for example, let us say how a synchronous generator will operate, the operating principle. So synchronous generator is also called alternator. Now suppose field is produced in the rotor, irrespective of the type of rotor, it may be cylindrical or it may be salient pole. Okay, so rotating magnetic field RMF is produced. Why? Because we will have DC excitation in the rotor and the rotor will be connected to the shaft. Now the shaft will rotate with some speed. So what will happen? The North Pole and South Pole, which is created by any type of the rotor, will rotate along the direction of the shaft, either clockwise or anti-clockwise. In any direction it will rotate. Now if we have rotating magnetic field in the produced due to the rotor, and this will cut the stator conductors. Now these stator conductors will have three-phase winding. Now since they have three-phase winding in the stator, we will have three-phase EMF or three-phase voltage which will be generated in the stator. So this is how a synchronous generator works, and this is simple. Okay. Now you see, this rotor will rotate at some frequency, say n. Okay, and the frequency with which this or the frequency of the EMF which is induced in the stator will be similar, okay? Suppose some frequency f is produced. Now the speed with respect to this f will be n. So this speed and this speed is same, okay? So that is the reason we call this type of machine as synchronous machines, okay? So basically this frequency depends on what is the speed of the rotor. That's what I want to say. It is also said, okay, that a synchronous generator is used in most of the power stations, okay? So this is very, very popular. This generator is very, very popular. And coming to synchronous motor, you see in synchronous motor what we do is similar to, we can analyze it similar to induction motor. See what will happen, the stator condition is same here. We will have three-phase supply given to the stator, due to which there will be rotating magnetic field produced due to the stator. But you see here in the rotor, we have north pole and south pole which is created, okay? Due to which what will happen is, this will not be a self-starting, okay? This will not be self-starting. So I'm not going deep into this particular topic, why is it not self-starting and how it is. What is important for us to understand is this synchronous motor is not self-starting, but to make it self-starting, what we can do is we can start it by short-circuiting the conductors. I mean, in how a induction motor starts. So we'll basically start this as an induction motor, and once the rotors have some speed, gain some speed, then we will get the excitation, and then ultimately what will happen is there will be locking between the rotating magnetic field of the stator and the field which is produced by the rotor. And thus what will happen is the rotor will start rotating at the synchronous speed, not below synchronous speed, which happens in induction motor, okay? So we'll start it as induction motor, but later we'll give the excitation and make the magnetic locking, and the rotor will rotate similar speed of the rotating magnetic field of the stator. Okay, so this is the basic principle which we can say, okay, or in a basic way in which we can visualize the synchronous machines. Okay, now coming to gate, what is important for gate is to understand the windings of the cylindrical rotor. Before I start with that, you see what happens is, we'll say alternator is there. So in alternator, the EMF is induced in the stator. We also call this EMF which is induced in the stator as excited EMF. Okay, excitation EMF. So you see, field is present. Okay, let us say this is my phi f. Now this phi f is nothing but which it is produced by the rotor. Okay. So now due to this phi f, what is happening is EF is produced. So we know by Lentz's law or Lentz's law and Faraday's law that the EMF which will be induced due to this particular flux will lag by 90 degrees. Okay. So this is my EF. Okay. Now the waveform of this flux is very, very important, and the waveform of this induced EMF depends on the waveform of this flux. Okay? Why? Because simple d phi by dt is happening. Okay? And it's very important for me or for us to have a sinusoidal flux, field flux, so that the induced EMF is sinusoidal, so that we do not have distortions in our induced EMF. If there is distortions in induced EMF, we will have harmonics in our voltage. Okay, we will have harmonics. So, in order to remove the harmonics, to have a smooth sinusoidal induced EMF in the stators, we need to have sinusoidal flux. So in cylindrical rotor, to have a sinusoidal flux, we know flux is nothing but MMF by reluctance. Now, in cylindrical rotor, what is happening is the reluctance is constant throughout the air gap. At any position, it does not depend with the position of the rotor. So what we can say is, this reluctance is anyways constant, so my flux is proportional to MMF. So the shape of the flux will depend on MMF. Okay. Now comes the concept of, let us understand the concept of, concentrated winding. Okay. So suppose, say, this is the rotor of the cylindrical rotor. Okay, this is a cylindrical rotor. Now suppose there are two slots. Okay, I want to have a two-pole rotor connection. So what I can do is, suppose I will take a coil. Okay, I will take a coil A dash, and I will wound this on this particular two slots. And suppose I'll take this and I'll put this A here, and then I will have certain amounts of turns. Suppose I make 3 turns out of this, and then ultimately I get A dash here. So per slot I'm having 3 turns in this particular case. Now when current will flow from A to A dash, which is I'm showing it here. So due to which, what will happen? I will have a north pole here and south pole here. I have already discussed in the earlier topics how to find out where is north pole and where is south pole. You see, we can use simple the right hand curls rule. So by right hand curls rule, we can see that the field which is produced here will be in this way, and here due to this it will be this way. So it will come out of the rotor from this position. So this is going to the north. Okay. Similarly, it is going inside the iron or the rotor at this particular position. Okay. So this particular part is stator. Okay. Now you see, this north pole and south pole is not sinusoidal throughout the air gap. It's not sinusoidal. So this particular types of slots or winding is called concentrated winding. Okay. So that means we will have 2 slots for 2 poles, and each slot will have, it may have more than 1 turns. It may have more than 1 turns. It may have as many as number of turns you want to give. You can give it. So the problem with the concentrated winding is the waveform of my flux will not be sinusoidal. Okay, it will be a typical square type of or trapezoidal type of waveform, but not at all sinusoidal. Okay. Now due to that, our flux waveform will deteriorate or deform or distort, and similarly our EF waveform will have some distortions, and due to which we'll have harmonics. Now how to improve that? That's the thing. Okay. So to improve that, the concept that we can use is, instead of having concentrated windings, we can have distributed windings. That means this particular situation is called distributed winding. So I have distributed the slots, one slot into many slots. So what happens is, now suppose I have a coil A dash. So I put it in various parts. Okay. So I have wound it in various ways. Okay. So it is now, what I have done is I've spread it throughout the cross section. So now you see the MMF which will be produced, okay, or the flux which will be produced will be better. Okay. So now what more you can do is, now suppose each slot has 1 turns or equal number of turns. Suppose each slot will have equal number of turns. So what will happen is, we will have the MMF, some step size MMF we'll have in this way. We'll have the MMF in step size. Further, we can improve this step size by increasing the number of slots. Okay. So if we further increase the number of slots, what will happen is my step size will improve and it will become further little bit triangular. Now we can improve that further by giving different number of turns at different position, and the number of turns can vary sinusoidally. Suppose here is I'm giving 2 turns here, 5 turns here, okay, and then 10 turns here. Similarly, I'm decreasing the turns. So what will happen is it will become something like that, and there will be very little steps. Small steps will be there in this way. Okay. And as the number of slots decreases, okay, as the number of slots increases, and number of turns also increases, so this step size will reduce, and we can achieve, somewhat, not completely sinusoidal, but we can achieve sinusoidal. And this is way better than the earlier, this type of flux, square type of flux, which we had earlier. Okay. So you see, what we have understood here is that distributed windings is a requirement, or it's necessary, so that our induced EMF, shape of the induced EMF gets better, so that the quality increases. Okay. But then once this happens, there is one disadvantage in this. So disadvantage here is nothing but, earlier my voltage, when I was having concentrated voltage, concentrated windings, so the EMF which was induced at a particular conductor and the other conductors were in phase. See, they all are at the same place. Okay. So we could have, what we did is, suppose the EMF induced by one coil is 1 volt. So, and suppose there are 10 conductors, 5 here and 5 here. So total EMF will be 10 into 1, that is 10 volts. So what we did is directly did the scalar addition, or directly we have added all the voltage what is induced in the conductor. Whereas here you see the induced EMF magnitude, RMF magnitude may be same, okay, but they at a particular instant they have some phase difference. Okay, so phase difference is. Now since they have phase difference, and when we will do the addition, vector addition, so the EMF will decrease from the scalar addition, what actually it was. Okay, and that decrement, okay, that means what I'm trying to tell is, if I have say 100 turns now, okay, or 100 conductors, okay, 100 conductors. Now each conductor is producing 1 volt, say. Now I cannot say that the total EMF produced is 100 volts. I cannot say, it will be less than that because of vector addition. How much less it will be, it depends, and it can be calculated, and that particular factor is known as distribution factor. Okay. So what we need to do basically is we have to multiply this distribution factor KD, which we know also as KD, okay, with induced EMF. And that will give me my actual induced EMF. Okay. So I have to multiply this KD factor. Now what is this KD factor? Okay. This KD, there is a formula to calculate KD, that is sine of M into gamma by 2 by M sine gamma by 2. Okay. So here M is nothing but number of slots per phase per pole, whereas this gamma is nothing but the slot pitch angle. That means if I have 48 slots, let us say, or 36 slots, let us say, in this way. So 360 divided by 36 will give me 10 degree mechanical. So gamma is 10 degree mechanical. But here, while we do this, it's very important, you can note it down, that we have to give the gamma electrical degree. So we need to find out the electrical degree. So electrical degree will be P by 2 into gamma mechanical. So if I have 2 poles, there is no problem, we can use that 10 degree. Suppose we have 4 poles, then this will become 20 degree electrical, which is very, very important, and this is where we can do silly mistakes. So before applying this formula here, we have to make sure that gamma is in electrical degree. Okay, so this is how we calculate KD. Okay, and there are questions in GATE where they have asked you to calculate this KD. They will give you the number of slots and turns, and those relations, by using those relations, you can solve this particular question. Okay, so this is why we have distribution, and this is and the reason why the EMF reduces is because of the vector addition. Okay, and this is how we calculate KD. Okay, now there is one more there is one more technique to remove some particular harmonics. Okay, suppose we need to remove, say, fifth harmonic. Fifth harmonic, I need to remove this. So there is a technique to do that. How to do that is, suppose my flux, I cannot say that my flux will be perfectly sinusoidal. There will be some distortions, and due to that distortion, suppose the fifth harmonic is that component which has the highest compared to other harmonics. Fifth harmonics is dominant. Okay. Now I want my EMF to be sinusoidal. That means I want my EMF, this fifth harmonic EMF, to be 0. And there is a technique to make the fifth harmonic of the EMF or any other harmonics, whichever is dominant, we can make that as 0. So that particular technique is called short pitched winding. So first of all, let us understand what is full pitch winding. Suppose it is a 2-pole winding. So what I can say is, suppose this is north pole and this is south pole. Let us say this is 2 poles. So if a slot is here, slot number 1, and say this is slot number, say this is slot number 2, 3, 4, 5. So this slot number 1 and slot number 5 are in full pitch. This is called full pitch winding. That means if I take a coil and if I put it in 1 and if I put, and it comes out from slot number 5, I will say that this is full pitch winding. Now if I put it in one side in 1 and it comes out from 4, then I will say it is short pitch winding. And this angle by which it short pitch is called beta. This is called short pitched angle. By how much I have short pitched my windings. Okay, and that factor. So what will happen is, ultimately if I short pitch again, my EMF will reduce. Okay, so induced EMF, again I have to multiply the induced EMF by a factor called Kp, which is the pitch factor, and this pitch factor is nothing but cos of beta by. Now this is for the fundamental EMF which is produced. For other harmonics which will be produced, other harmonic EMF, suppose induced EMF for third harmonics will be nothing but EMF into third harmonics into, we have to multiply this Kp and Kd for the third harmonic. So Kd also we can calculate for third harmonic. So we have to just multiply n with gamma. Similarly, here what we have to do is Kp for third harmonics. That means Kp for third harmonics will be cos of 3 into beta by 2. Similarly, Kp for fifth harmonic will be cos of 5 beta by 2. So this is how we can calculate Kp. Okay. Now you see, again we have to consider that concept that suppose this is my, suppose it is said that the question will come in this way. Okay, they will say that there are say there are 36 slots and my coils are short pitched by 2 slots, short pitched by 2 slot pitch. So calculate the induced EMF. So for that you need to find out KD, you need to find out KP. So I'll show how to find out KP here. So you see, and it is also said that suppose this is 4-pole connection, 4-pole winding of the rotor. So if it is 4-pole winding of the rotor, how to calculate this 2 slot pitch? So we need to calculate beta. Now beta is nothing but the short pitched angle. So they have said that the short pitch is by 2 slot pitch. So we need to find out, that means beta is nothing but 2 times of gamma. Okay, now we need to find out gamma. So gamma is nothing but 360 by 36, which is 10 degree, which is already calculated. Now this is mechanical. So electrical, we know it is 4 poles, so it will become 20 degree. So here it will become 20 into 2, 40 degree. So beta electrical is 40 degree. So the pitch factor Kp will be nothing but cos of 40 by 2, that is cos of 20 degree. So this is how we can find out the Kp, as well as we can find out Kd also, because we have gamma. So M also we can find out. M is nothing but number of slots, which is 30 slots per pole. Per pole means number of poles are 4. Per phase, this is 3-phase connection. So 4 into 3. So this is 4 to 3 is 12. 12 3 is a 36. So if M is there, so similarly we can find out Kd also, because it will be sine of 60 by 2, that means sine of 30 divided by 3 sine of 10. Okay, so by that way we can find out Kd and Kp. Now let us say we need to, the questions may be in this way also. They will ask what should be the by how many slot pitch we should have the short pitch of that winding, so that the fifth harmonic is fifth harmonic is 0. So for the fifth harmonic to be 0, first of all what we need to do is we need to find out cos 5 by 2 should be 0, or Kp should be 0. So if Kp is 0, then definitely my induced EMF for the fifth harmonic will become 0. That is one technique. So by using this technique, we can remove this fifth harmonic. Okay. So now let us find out what is beta for that. So we know that this is 0 when this is cos of 90 degree. So I can say that 5 beta by 2 is equal to 90 degree. So I can say beta is equal to 5. Okay. 1 and 40, 5 is a 40, so 30 into 16, 36 degrees. Okay. So if beta electrical is, so this is electrical degree. So if beta electrical is 36 degree, now how we bring it, that is up to us. So for different machines, it will be different conditions, different number of slots. We will have different slot pitches. But if after calculation we get beta electrical is 36 degree for any particular machine, the fifth harmonic of that machine will be 0. Okay. So this is, you see, the application of Kd and Kp. Okay. So I don't want to go to the much details in this particular topic. Rather, I will go back to the phasor again. Okay, from which we actually started discussing this Kd, Kp. So this is the phasor. Now you see, this is my flux, and the EMF which is induced will lag 90 degree. So see, whatever is induced due to that, so reason will always lead the cause. Always remember this. Okay. So here the reason is this flux, and the effect or the result is the induced EMF. So that is why induced EMF will lag 90 degree. Lag means going clockwise. So you see, this is going clockwise 90 degree. Okay. So this is the basic phasor of alternator. Similarly, if you see for motors, In motor, what we do is we give supply, okay? And after giving supply, let us say we have, we will have some E. Okay, we can see that in that particular way. I particularly see this motor phasor in this way, that we give supply into the stator, due to which there is some induced EMF in the windings of the stator, and due to which there is flux. Okay, I see it particularly in this way. It becomes easier for us to visualize. So here you see this is the supply, or this is the reason, and this is what is produced in the or the field which is produced due to this particular induced EMF. Okay, so now you see, if we know what is armature reaction. Okay, so armature reaction is nothing, basically, you see, suppose we have current in the armature, okay, and that current is, say, 0 power factor lagging. So 0 power factor lagging with respect to the induced EMF EF. Okay, so we all know that we can draw the equivalent circuit of this synchronous mode, let us say alternator, in this particular way. Suppose this is load, so this is my EF, and this is the current IA. Now suppose the angle between IA and EF is 90 degree, okay, 90 degree lagging because of this particular load. Okay, 0 power factor load is there. So this will be my IA, 90 degree lagging. And I know that field which is produced by the current will be in phase with the current. So I can say this is my field phi A. Now you see this phi A is directly opposite to the field. Directly opposite to the field. So I can say that for 0 power factor lagging, the armature reaction, what it is doing is it is demagnetizing my field. Okay, it is demagnetizing because it is opposite to the field. So I can say that this, due to this, is demagnetizing. So what it will do is, see, this induced EMF is proportional to the field flux phi F. Okay? Now if this comes opposite to this, so what will happen is this field will reduce. So this will, the total resultant will reduce. So if the resultant is reduced, this value will come down. Yes or no? This value will come down. Now suppose, let us say that this particular generator, this is generator, and this is suppose connected to a bus bar, and the load is again connected to a bus bar. So we need to maintain a particular voltage in the bus bar. So if we need to if we need to maintain particular current in the bus bar, so let us say we don't want, or in other words, I don't want this EF to fall down. So what will happen is, if I have demagnetizing armature reaction, but I don't want this to fall down, so ultimately I want this to increase. My field flux should increase so that it compensates the demagnetization. And thus I can relate this to over excitation. That means whenever I will have a lagging load, okay, a lagging load, whenever I will have a lagging load, I will have demagnetization in alternator, and this demagnetization will result in over excitation of the. Similarly in motor, let us see what will happen. In motor, if I have a load which is lagging, now in motor what happens is, it's this way. This is my supply, let us say, and these are the parameters of the motor itself, and this is my EF. Now current, suppose this is VT. Now in VT, across the terminals of the stator, we have connected a supply. Now current will flow IA in this way, and this is my EF. Now suppose the angle between the current which is flowing and the EF is 90 degree lagging. Suppose the current is 90 degree lagging. So if the current is 90 degree lagging, suppose in this way IA, okay. So what will happen here, the field that is produced phi A due to current is in phase with the field, okay, phi M. So therefore I can say that lagging zero power factor, lagging in motor is having magnetizing effect. Okay. Now you see what will happen is my EF will increase. Okay. Now suppose I don't want my EF to increase. So what I can do is I can reduce my field excitation. So if I reduce my field excitation, it will become under excited. So this is how we can relate, you see, excitation, under excitation and over excitation in alternator and motor. Similarly, you see, if I have a leading load here, it will be magnetizing and then it will become under excited in alternator. Similarly, in motor, if I have a leading load, what will happen? It will be demagnetizing. So a leading load will be demagnetizing. If it is demagnetizing, then definitely it is over excited. Okay. Similarly, if it is unity power factor, okay, unity power factor along EF itself, then what will happen is it will be cross magnetizing. So in that case, if it is say cross magnetizing, the value of the shape of the phi will distort, but the value will not change appreciably, and in that case we can say that it is normally excited. Okay. So the excitation will be normal, will not change the excitation. So this is how we can relate the excitations to the phasors. Okay. And now it is very, very important, you see, to understand these concepts and relate these concepts, which is very, very important. If you cannot relate the concepts in synchronous machines, it will be very difficult to study this topic. Now you see, if I want to draw the phasor now, suppose this is my phi F and say this is my EF. Okay. Now I will have a voltage at the terminal and that voltage will always lag this induced EMF. Why? Because now see, this is my EF and this is my load and this is my VT. Okay. So suppose some resistance RA is there and some reactance excess, synchronous reactance is there excess, and some current is flowing IA. Okay. So the VT will always have to lag this particular induced EMF. Why? Because this is produced due to this. Okay. So this will always lag VT. What will be the value we will see later? Okay, that will depend on the current actually. So let us say this angle between VT and EF is called the del angle. Okay. Now suppose the current IA with respect to VT, let us see. Let us see if the current is lagging with respect to VT. That means my current is somewhere here, IA. And the theta, this theta is nothing but the power factor angle, output power factor angle or load power factor angle. Okay, that means IA and omega. This theta is between IA and VT. The angle between EF and IA is basically called the internal power factor angle. Okay, and we represent that by sun. Okay. Now you see, if we write the equation here, it will be EF is equal to VT plus IA into RA plus J. So now let us draw it. Okay. So if we try to draw, now I don't know how much my EF is. Let me calculate my EF. So this is VT. Now VT plus IRA. So IA is along this side. So my IRA will also be along this side. So let us say this much is IA RA. This is VT. Now after IARA, I will add this with J into XS into IA. So J means nothing but 90 degree anti-clockwise operator, plus 90. So plus 90 means this side. So I'll go anti-clockwise. So from here, I'll rotate anti-clockwise along this side. And suppose this is J, IA, axis. Now what I will do is, from this point, I will add this point. So this is this is how I can draw the phasor of a lagging current for an alternator. I also can find out the magnitude of the EF, okay? And this is very, very useful for the analysis and calculation. You see, what we have to do is we have to extend this IA and this extend this particular thing. So you see, I know this angle is 90 degree and this line is parallel to this line, so this angle is also 90 degree. Now let us say this is O, this is A, this is B. So I can say that OAB is a right angle triangle. Okay, so and such that AB or OB is perpendicular to AB. So I can say that OA square is equal to OB square plus AB square. Now here OB is nothing but, see, up to here it is VT, so this much will become my VT cos of theta. Okay, and this much I know it is nothing but IARA. So I can say this is VT cos theta plus IARA whole square plus AB square. Now AB is this. Now here, up to here I know it is IA axis, the length, and this is nothing but VT sin theta. So I can say this is VT sin theta plus IA axis whole square. And this is nothing but EF square. So we can get the magnitude of the induced EMF from this particular equation. Now this is for a lagging load. Now you see, if I have a leading load, the only difference, if you do the calculation, same analysis, the only difference will be this plus will become minus. Okay. So there is a technique to remember when it will be plus and when it will be minus. This will be same. Okay. This part will be same. So let us say I try to remember this particular formula. So I know that if it is lagging, how to remember it? I'm giving a technique to remember this. So if it is lagging, so lagging means we know it is demagnetizing. And if it is demagnetizing, we know it should be overexcited. So for a lagging load, my EF value should be more. In that way you can remember. So more means I should have a plus here. So that means for lagging load, I should have a plus. For leading load, it is magnetizing in alternator. So if it is magnetizing, I know it is underexcited. So my EF value will be less. So EF value will be minus for leading load. For example, for unity power factor. Now unity power factor output will be cos theta will become 1, sin theta will become 0. So whatever plus or minus is here, it doesn't matter. Okay. So this formula is very, very useful. Very, very useful. As far as gate numerical is concerned. Similarly, we can find out for the motor also. In motor, this will become Vt cos theta minus IR. And rest here the technique will be same. If it is demagnetizing, it will be plus. If it is magnetizing, it will be minus. So that's it. So this is how we need to visualize the synchronous machines and go forward. Now once we go forward this, we can find out the current expression from this particular topic. Okay. And once we find the current and the induced EMF, this is immensely helpful and useful for solving gate questions. Also, we can find out the power equations. Okay, the power equations, basically they will ask you for the lossless equations. And lossless power equations, P input is equal to P output. Lossless means where the RA becomes 0. And in most of the gate questions, they will say, or rather all the gate questions in synchronous machines, they will mention that it is a lossless case. And if it becomes a lossless case, my input power becomes equal to output power, and that is nothing but ET into EF into VT by XS sine del. Okay, this is the power. Okay, now whether it is a motor or generator or input power or output power, the expression is same. Okay, similarly you can find out the reactive input power of the motor or reactive output of generator. See, there is no meaning of reactive output of a motor. Okay, there is no meaning in that, because the output of a motor is mechanical. So we are concerned with the, since mechanical energy which is converted is the real energy, so we will be concerned with the real output power of a motor. Whereas input of a motor will be electrical. Now, electrical input can be real and reactive both. So we need to find out the Q input of motor. Similarly, the output of a generator will be electrical, so we will be bothered with, we need to find out Q output of the generator or alternator. Similarly, the input of a alternator or a generator is real input. We give real mechanical input. Mechanical input is nothing but the real input. So we are not bothered about finding what is Qi of G. Okay, this is practically this is useless. Okay, this value will be useless. Theoretically, we can find the value, but it will not be of any use. So in this way, if you can find out and if you can understand the power equation, reactive value, and then going forward, you can understand the V curve and the inverted V curve. So once you get these things correctly, this is how we analyze a synchronous machine for cylindrical rotor. Also, we can calculate the voltage regulations. Okay, there are various techniques and methods which I will discuss in other videos. So for now, let us stick back to this particular basic, and I hope this whatever I have discussed now, this will help you to visualize it in a very in a better way. And with this, I conclude my topic. Best of luck to all of you for your GATE exam.